Hello everyone. Welcome to week 9 of problem solving session for uh, Analog Electronic Circuits in NPTL and myself Chaitanya Kumar from Department of Electrical Engineering IT Madras. So before we start the content of week 9, can you guys share if you have any issues or any doubts in the content so far in the course? Okay, so if there is no doubt, we will begin with some problems based on the week's material. So we will start with various topologies of fully differential amplifiers and see the pros and cons of these topologies. So let's first of all understand what is a fully differential amplifier. So uh, let's consider this gain block which takes input as some V common mode plus Vd by 2 and V common mode minus Vd by 2 and gives an output of V out. So this is a differential to single-ended amplifier. And let's say we have another kind of amplifier that takes input as VCM plus VD by 2 and VCM minus VD by 2 and gives us the output as VCM out plus VO by 2 and VCM out minus VO by 2. So, in this case, the input is basically the taken as the difference between the two lines that we have, that is VT, and the output that we have is the difference between the two output lines, that is V out. So, this is a fully differential amplifier. So, what is basically the pros of this fully differential amplifier is that the noise that rides on the common mode of input and output can be omitted altogether. And hence, since we are only taking the difference between the two lines, so let's say there is a common disturbance coming due to power supply variation or any electromagnetic coupling onto the signal lines. And since the signal lines are very close by in the chip, so in that case, what will happen is that external disturbance will affect both the signal lines in the similar way. And since you are taking the difference as the input as the signal on that signal line, so that thing can be cancelled. So that effect will be cancelled. And one of the most important, so this basically this kind of a fully differential amplifier block can be used in multiple places in a signal chain. So you can make a complete fully differential signal chain. So where you will have cascade of several amplifiers, one after each other. So one of the most important property of these signal chain is one important advantage in this kind of fully differential signal chain is this fully differential signal chain is that let's say you want to invert the signal. In case you have a like single-ended chain, in that case, so let's see how inversion is possible. To invert the signal in single-ended chains, single-ended chain, you will basically need analog amp. buffer with a gain of -1. How will we build that? So, any idea how we will build analog buffer with a gain of -1? So, one of the most common circuit to do this is an inverting amplifier. So, this kind of circuit we need to use. So, if we have input as Vi, the output will be minus of the feedback resistor divided by the input resistor, that is minus R by R times Vi, which will be equal to minus Vi. So this is how you achieve inversion in a single-ended system. Now, what will be the issue with this? You will basically add the noise of R and the op amp. You will need to burn power in the op amp. So it will basically add its own noise and distortion, and it will burn some amount of power to achieve this inversion with with the desirable signal to noise ratio. However, if we see the differential ended in differential ended scenario, we can just, for example, we have VCM plus VD by 2 and VCM minus VD by 2. So here if we take the difference between two, the difference is VD, and we just cross these lines, and now the difference that we take is minus VD. So there is no power that needs to be burned, or there is no noise that gets injected due to an actual circuit that performs inversion. You can just get inversion with the help of so inversion basically you get as free. So this is one of the key important feature of fully differential circuits. So now that we have some motivation behind why do we need fully differential circuits, we will see that how these fully differential circuits are realized. So one of the most straightforward way and other thing, okay. So we saw that this is how we connect multiple fully differential circuits. And let's say if we only see, so the let's say we have VD in over here, and then we have VD1, then we have VD2 at the output of second stage, and finally we have VD3. So this is the differential signal. Now there will be some common mode signal for VCM1, let's say, and then there we will have some VCM2, we will have VCM3, and we will have VCM4. Now, since all these devices are made of active components, and the common mode basically signifies what kind, the operating point of those active components. So there is a certain range of common mode within which this particular circuit can work without problems, and it would not inject distortion of its own. So we need to make sure that going down the signal chain, if let's say there is some disturbance in the input common mode, we need to make sure that this input common mode disturbance should not propagate in the signal chain, because even though we say that the differential lines are immune to common mode, but since this common mode decides the operating point of the devices that are present in this block, so if the common mode varies too much, that can basically inject some amount of nonlinearity on the differential signal. So we need to make sure, and moreover, let's say if the common mode swing, let's say due to some faulty design, keeps on getting amplified as we go amongst the signal chain. So in that case, what will happen is till the time we reach the end of the signal chain, the common mode swing can be so much that it can just drive the latter stages out of saturation and can make your signal chain useless. So we need to make sure that the differential gain that we get is basically an amplification or let's say a specific gain that we need that is present, and at the same time the common mode gain, the common mode swing, let's say there is some common mode swing over here, that should keep on getting attenuated as we move further down the signal chain. So this is one of the important characteristic of the fully differential amplifier, that is basically that is also called common mode rejection ratio, which is basically equal to the ratio of the differential mode gain divided by the ratio of the common mode gain. And ideally, it should be infinite. So there should not be any kind of common mode which is being passed out to the output. So I hope this gives us some block level background of fully differential circuit. Any doubt so far? I am audible, right? Okay, so if can anyone confirm that I'm yeah, okay? I'm audible, and is there any doubt in explanation so far? Okay, so if there is no other doubt, we will move forward. So we will look at some topologies of these kind of signals, these kind of amplifiers. So one of the basic amplifier, so we will see topology one. So we are now talking about fully differential amplifiers. So it should take fully differential input, let's say VCM plus VD by 2, VB, VCM minus VD by 2. This is some VDD. This is resistor. And here we have some current 2I and equal current of value I and I flows in both the branches. So this is the basic topology of fully differential amplifier. We have VCMO plus VO. Can you help me determine the sign of the outputs? So if this is VCM plus VD by 2 and this is VCM minus VD by 2, so let's call this as node 1, let's call this as node 2. So what will node 1 have? The sign of the differential signal that is riding on it. Can someone tell me what inverting on the left side? Correct. So node 2 will basically have inverting uh, stuff. So we will have on node 2, we will have VCM out minus V out by 2 and VCM out plus V out by 2. No, so let's say the gain of this transistor is GM, and we have this resistor R over here. So what is basically the differential gain? What we will have to do in order to find out the gain, we will have to draw the differential half circuit of this structure. And how will we draw differential half circuit? This tail current will basically behave as a virtual ground or differential ground. So this is just nothing but differential half circuit. So differential half circuit basically looks like this. We have R over here. We have some GM, and this is grounded. And if we have VCM plus VD by 2 over here, so VCM we can drop for now because we are just looking at the differential half circuit. So VD by 2, or since we are folding this, so we will consider this VD, and we have V out over here. What is the ratio, the magnitude of VO by VD? It's basically equal to, this is equal to, so this is equal to basically the gain of this is a common source topology, and the magnitude of gain is basically GM times R. So this is what we get as the differential gain, that is the output differential voltage minus the input differential voltage is basically GM times R. And as I said, here the sign basically can be inverted quite easily. So since the sign can be inverted quite easily, so basically we need not to worry about the sign. We can just consider node 1 as the positive terminal and node 2 as the negative terminal of the output, and get a positive gain, that is of GM times R. Okay, so we got this gain of GM times R. Now, once we got this gain in differential half circuit, can you guys help me solve common mode half circuit? So, like here, what we did, we considered in differential half circuit, we considered this at virtual ground, and we just analyzed one side, and the other side will also work in same, but like magnitude wise, it will be same, and it will be negative of that. So that's how we analyze differential half circuit. In common mode half circuit, what we do is we basically through across the line of symmetry, we fold this. We fold this topology. So that results in the following circuit. We have R by 2 over here. We have GM by 2 GM as the volt as the current as the input transistor, and we have one more circuit down over here. So, can you guys help me in finding out the gain from input common mode to the output common mode, that is VCMO? Can you guys help me do that? So we have to find out VCM O by VCM. How we will find out? So basically, first of all, the gain from VCM to, let's say, call this VCMT, denoting the swing at the tail node. Yeah, that will basically be so if the input resistance of this lower current sources are not, so we will have 2 GM R naught upon 1 plus GM R naught. This will be the voltage at this node times VCM. So the current that will flow through this branch will be 2 GM R naught upon 1 plus GM R naught times VCM divided by R naught. So this can be cancelled, and we finally get as, so 2 GM VCM divided by 1 plus GM R naught. This is VC. This is the current that we are trying to find. So this is equal to, and this can roughly be called as GMR naught. So 2 VCM by R naught is what we get. So now basically now VCMO can be written as that resistor R by 2 multiplied by the incremental common mode current that we have. Let's call this ICM. Okay. So this basically gives us VCMO as 2 VCM by R naught. So this is equal to R by R naught times VCM. Okay. So the gain of common mode, so VCM O by VCM is basically equal to R by R naught. And the gain of differential mode we found out as GMR. So what is the common mode rejection ratio? It's basically the gain of the differential mode circuit, that is GMR, divided by the gain of the common mode circuit, that is R by R naught. This comes out to be GM times R naught. Okay. So we can see over here that if R naught is infinity, if the R naught, that is the resistance of the tail current, is infinite, in that case there won't be the common mode rejection ratio will become infinite. That means to say that no matter what common mode swing we have at the input, it won't be reflected at the output common mode swing. Okay. So if the tail current source was infinite, in that case we would have got a better we would have got a better this thing a better CMRR in this differential amplifier. Okay, I hope this is clear.
Yes, sir.
Okay. Now let's see. So this RO is basically a device specific quantity, and you can't do much to help this RO. You can increase its length to some extent, but after that, there is not much you can do about it. So if we see that. So there is, let's see if there is any other way to help increase the output resistance, increase the CMRR. So one
Sir,
more
we can
thing,
increase R naught with the help of ID now.
sorry,
We can increase ID, then R naught will increase now.
ID as in
Means R naught is
what you
equal
are
to
referring to.
1 by lambda times of ID, right?
Yeah, so 1 by lambda times ID, you have to reduce ID, but the problem by reducing ID is the ID is not fixed by whatever, so ID is fixed by whatever GM you need over here. So that you can't change. Till to some extent, you can increase the value of lambda by basically increasing the basically increasing the length of the transistor, but that also will saturate after some point. And then if you increase the length of the transistor too much, then you will have parasitic capacitances that will kill your gain at very high frequencies.
Yes, sir.
Yeah. And as far as cascode is concerned, cascode is not possible because that will take a huge amount of headroom in this thing. Because already you have three element stack, and putting one more thing won't make too much sense. Okay, so we see that we can get so much CMRR from this. Now let's see.
Sir,
Yeah.
so if you don't mind, Sir, could you repeat again that VCM by not by VCM, sir?
VCM
I'm
not by VCM.
understandable. Differential gain, I'm understandable. Sir, common mode gain, I'm getting confused every time.
So which part did you get confused?
From I mean in general, while you are finding, we need to for CMMR, we will find out the differential gain by common mode gain, right? Whenever if
Yeah.
you want to find out the common mode gain, for every any circuit, how should we approach?
So uh, across along the axis of symmetry, you fold the circuit on top of each other. So if you do that, the two resistance will come in parallel to each other. So you will have R by 2 over here. You will have two transistors in parallel to each other that will result in 2 GM. And then you have this current source is a single current source. So you will have basically, so let's say its output resistance was R naught. So you have one R naught over here. And what you need to do is from input to output, now like any other incremental analysis, you need to find out the gain.
Sir, if circuit is not symmetric, at the time how should we proceed, sir?
If circuit, so in a fully differential circuit, so let's say there was some error between these two. So this was R, so if this was R, this was R by some R1. In that case, you can't basically use this approach straightforwardly because when the circuit is completely symmetric, then only you will have this notion that common mode and differential gain, common mode swing and differential swing can be separated. If the circuit is not symmetric, in that case, what will happen is if there is some common mode swing at the input, some of that will leak at the output in differential fashion also. So common mode swing at the input will result in some differential swing at the output. So there you can't use this method. The circuit has to be symmetric for you to do this.
Yes, sir. Perfect, sir. Sir, if circuit is not symmetric, I know how to find out the differential gain, sir. But I am then getting confused how to find out that common mode
No,
gain.
in that case, you will have to basically. There is no. So there you will have to basically. So like differential gain, whatever differential gain. So like for a perfectly symmetric circuit, you will basically have common mode. So gain between output common mode and input common mode. This will be some non-zero quantity. A differential mode will be a non-zero quantity, but the cross things, a common mode differential mode will be zero, and a differential mode common mode will be zero. But if the circuit is non-symmetric, these two quantities will also be non-zero. So you need to find all the gains.
Yes, sir. Sir, can we do with five transistor logic, sir? I will get more clarity.
Currently, I'm just focusing on fully differential. The five transistor stuff is pursue like a differential to single-ended circuit.
Yes, sir.
So there, in output, there is no this thing. In output, there is no there is no common mode and differential mode. It's just one signal.
No, sir. At the time also, you will apply in small signal analysis. We will differentiate small, medium.
No, a small signal analysis you will apply. Okay, let's try to do that as well. So we have VCM plus VD by 2. and we have some VB, some output resistance R naught, and we have V out over here, and VCM minus VD by 2. Okay, so this is our common 5 transistor circuit. Now in this 5 transistor circuit, let's say we have some GM over here, some GM over here. The output resistance of NMOSes, let's say, is infinite, and there is some ROP and some ROP over here. Okay, so in this case, you can see circuit is not symmetric. So basically, what all gains you will have, like earlier we discussed that we will have 4 kinds of gain. So in this case, since output is a simple output is a single-ended node, so what all uh, gains we will have? We will have a output to differential mode thing. That will be a non-zero quantity, and we will have a output to common mode thing that will be a non-zero quantity. Okay, so this kind of circuit we will have, and you need to basically find out the gain from the differential input to output separately, and gain from differential common mode input to output separately. Okay, so what you will do is, first of all, let's try to find out different output to differential mode gain. So in output to differential mode gain, again, since if we look only at the lower end of the circuit, in the lower end of the circuit, basically you can see that since looking up here, the gain of the impedance from both the ends is the same, that is of 1 by GM. That means to say that in the lower end of the circuit, both the halves are symmetric. So this will be sitting at differential 0 volts, correct? You understand that?
Yes, sir. Yes, sir. Following, sir.
Yeah. So basically, you need to see wherever the symmetry is applied, you have to follow that symmetry. So we are analyzing the differential part first. So here there will be zero voltage. So how your circuit will look for the VD part? You will have VD by 2 over here. And this is basically the differential ground. And here you have the output. Okay. You have some ROP over here, and here minus VD by 2. Okay. Now what you can do is you can basically you can basically try to find out the Norton equivalent at the output. So first of all, for Norton equivalent, you will find the short circuit current. To find out the short circuit current, you will just put it to ground, and you will find out the ISC over here. If you try to find out ISC, what you will get? So some current will be pulled by this. What will be the current that will be pulled by this node, this transistor?
Sir, GM into ROP.
GM into the current minus
Yeah.
GM times VD by 2.
Okay. Yes, sir. Yes, sir.
So one part is, so ISC is equal to minus Gm times Vd by 2, and there will be some current that will be pushed from the top into this circuit. What will be pushed or pulled from top into this circuit? How will this current what will be the mechanism for that? So here we have Vd by 2. So if we have Vd by 2 over here, so a current of Gm times Vd by 2 will be pulled from this side. Okay. That means to say, so that will basically create, so when this current will be pulled from here, the now that current will be divided between ROP and what is the looking in impedance over here?
1 by GM, sir.
1 by GM. So where will be the most of the current go?
Sir, it will go by 1 by GM only
1 by
because 1 by
GM.
GM
So
is
if
small.
most of the current is going in 1 by GM, the same current will be mirrored in the opposite side PMOS, right?
Yes, sir.
Okay, so if that is the case, that means to say the current that will be pushed from here. Okay, the current that will be pushed from here will be
GM
the
VD by
same
2, sir.
current that was being pulled, GM Vd by 2. Okay. So a current of Gm minus Gm Vd by 2 is being pulled by transistor 2. That means to say this current is pushing Gm Vd by 2 inside. If it is pulling minus Gm Vd by 2, that means it is pushing Gm Vd by 2. Okay. So GMVD by 2 is being pushed from upper side, the PMOS side, and GMVD by 2 is being pushed from the NMOS side. So the total current that we have is basically GMVD by 2 plus GMVD by 2. That means to say GM times VD. Okay.
Yes, sir.
Okay. So the short circuit current is found out. Now, what is the Thevenin resistance looking in over here
From where, sir?
at the output? P over here, and here you have VD by 2 minus VD by 2. So, what is the impedance Z out?
Sir, uh, ROP, sir.
ROP. Okay. So, V out you have as the short circuit current multiplied by the output resistance. Correct?
Yes, sir. Okay.
So you have GM times ROP times VD. You understand this?
Yes, sir.
Okay. Now, if you have GM times ROP times VD, this you have found out the differential. So the impact the differential input will have on the output. Correct? So what did you do? You applied the principle of differential symmetry and common mode symmetry till that time where the circuit was symmetrical. So like in the upper case where there was fully differential circuit, you basically made the complete differential half as one particular circuit. Okay, this became a pure common source circuit. But in the second case, where the circuit was not symmetrical in the top, what you had was that till the place the circuit was symmetrical, you applied the principle of differential half circuit, and on top of that, you let the circuit remain as it is. You understand?
Yes, sir.
Okay. Now let's see the common mode half circuit. The what will happen in common mode case? So you have VCM over here, V bias, then VCM over here. So basically, you will be able to join the nodes that are swinging in the same fashion. Now, this node is already joined. Can this node be joined with each other?
No, sir.
Why? Because here there will be the swing will be basically GMP by GMN, sorry, GMN by GMP, which will be much smaller by the swing over here, that is GMN times ROP. Okay, so here you can't basically fold it and make it a differential circuit. So basically, what we are doing over here, we are applying the position of we are applying the principle of superposition. While doing incremental analysis, we know that the circuit is linear, and if the circuit is linear, we can apply principle of superposition. In the first case, we assumed that VCM is zero and we have only VD. We found out the output due to only VD. Now, in second case, what we will do is we will assume VD is zero and we have only VCM. Okay, you understand?
Yes, sir. Yes. Following, sir.
Okay. Now again, here now since there is no symmetry about the axis, you have VCM on transistor 1 and VCM on transistor 2. So again, you can apply principle of superposition to get the output that is V out over here. So first of all, we will assume that there is no VCM on transistor 2 and VCM, there is only swing on transistor 1. In that case, what will happen? So we have VB over here. VB is a biasing voltage, so this is grounded, and some output resistance RO over here. Here we have VCM. And since we are saying that there is no, so this is AC ground or incremental ground. Okay. So now this is how your circuit looks. You have ROP over here and ROP over here. Okay. Now, this circuit is grounded. So, looking in from here, can you tell me what is the impedance that we are seeing?
1/GM, sir.
Just a minute. So, basically, we have 1 by GM parallel R out.
Ah, yes, sir.
Correct?
Yes, sir.
So, what is the voltage over here then?
0, sir.
Huh? Why 0?
Here VB and grounded, no, sir.
So
No, no,
what?
no. VS voltage.
Yeah.
We'll write equivalent. It will be.
Basically, this is acting, this complete stuff over here is acting
Source
as a
degenerated.
source degeneration. So how does it looks like? You have
1 by
VCM
2.
over here,
Yes, sir.
and here you have an impedance, an equivalent impedance of 1 by GM parallel, the
Or
output
not.
resistance R out, correct?
Mm.
Okay, which is roughly equal to 1 by GM.
Yes, sir.
Okay, now if that is the case, what is the voltage at this node, the source node?
Voltage. So GM into ROP 1 plus GM into
GM into
ROP, sir.
what is ROP?
Uh, Output resistance of PMOS.
Where is PMOS?
Uh, okay, okay. Sorry, from drain side also unit that
No,
ROP and
the resistance of this thing is the resistance of the NMOS is infinite, no?
okay.
Hey, come on, man. This has been discussed so many times.
Yes, sir. Yes, sir. Sir, it should be unity, sir.
How it will
Like,
be unity? In what case it is unity?
ideal case, sir.
What is the ideal case?
Oh, okay. R naught will be not present.
R naught will be.
Infinity, sir.
If R naught is infinity, what is the source resistance here?
1 by GM, sir. Oh,
1 by GM. So if the source, okay, you tell me just this. If this is GM, this is input of VCM, and this is some RS. So what will be the voltage at this node?
sir, GM into RS
GM into RS
1 plus divided by
divided by
1 plus
1 plus
GM into
GM into.
that drain resistance.
Why drain
Infinity line.
resistance will come over here? That's GMRS upon 1 plus GMRS. I have told you several times to remember this. So basically, you should
Yes, sir.
remember these gains and impedances, output impedances of these three basic blocks at least: common source, common drain, and common gate. Okay. If you remember these things, circuit analysis will become very easy. Otherwise, every time you will have to apply KCL, KVL in each new circuit that you see. If you remember these things, you can identify these patterns. For example, here we saw, here we identified that this basically works as a, if the resistance over here is infinite, this basically works as a common drain amplifier. You could have easily said that, okay, it's GMRS upon 1 plus GMRS, if you remember that. Then over here, you could have found out the gain. So it's really advisable to remember input impedance, output impedance, and gain for these three kind of circuits, these three configurations of MOSFET. Okay.
Good, sir. Yes, sir. Yes.
Okay. So if this is GMRS upon 1 plus GMRS, and the RS in this case is what? 1 by GM. So that means to say the voltage at this node will be GM upon 1 by GM divided by 1 plus GM up by GM. Correct?
Yes, sir. 1 by
Okay.
2.
That is basically VCM by 2. Okay.
Yes, sir.
Okay, so if this voltage is VCM by 2, this voltage is VCM by 2. What will be the current that will be flowing?
Sir, VCM by 2 by or not? I equal to
VCM by 2
by 2 or not? Yes, sir.
R naught. VCM by 2 R naught. Correct?
Yes, sir.
If this is VCM by 2 R naught, so that current will be equally divided between these two branches.
Yes, sir.
Why?
It won't, sir. Current will be equally divided because of the same bias voltage.
What bias voltage?
No, no.
See, looking in from here, this impedance
Mm.
and this impedance is exactly equal. So the current that is VCM by 2 R naught will be equally divided between the two branches. You
Yes, sir.
follow?
Yes, sir.
Okay, so in this case, what will be the voltage? So here, so VCM by 4 R naught will flow in this direction, and VCM by 4 R naught will flow in this direction through the current mirror. So overall, VCM by 2 R naught will be the short circuit current that will be drawn from the output, and that multiplied by the output resistance ROP will give you the common mode gain at the output. You understand?
Yes, sir.
So for one half of the circuit, the gain will be so VCM out 1. So VCM out 1 will be equal to VCM by 2 R naught times ROP. Okay.
Yes, sir.
Okay. Now the same thing you will do. You will ground this particular part. This you will ground the transistor one's gate, and you will give VCM to transistor two's gate. And it will turn out that if you say that VCM O2 will also be equal to the same voltage. Okay.
Yes, sir.
And if that is the case, your overall VCM out
VCM by R
will
not, sir.
be
Not.
VCM times ROP by R naught.
Yes, sir.
Okay. So you basically like whether the circuit is symmetric or not symmetric, you can always apply principle of superposition. And when you apply this principle of superposition, in first case you take the only differential part of the signal, input signal, and find out the output signal. And in that case, you should keep in mind that wherever the circuit is symmetric and two opposite nodes are being joined to each other, you can ground it. Okay, for example, this node over here, and then proceed accordingly. So this is how you proceed for the differential part of the circuit. For the common mode part of the circuit, what you do is so since you can't fold the complete circuit, you can basically apply superposition once again. You give the common mode to one half of the circuit, you give the common mode to the other half of the circuit. In both case, find out the output voltage or current, whatever you need to find out, and then add the two.
Yes, sir.
Okay. So VCM out due to the common mode. So basically, the output due to the common mode is VCM ROP by R naught, and the output voltage due to differential mode was GM times ROP times VD. So overall V out we get as VCM ROP by R naught plus VD GM times RO. Okay. So can you tell me which will be the dominating quantity over here?
Differential, sir.
The differential one. Why? Because only thing that is different between the differential quantity and the common mode quantity is we have 1 by
GM.
RO over here and GM over here. And ideally, your GM is much larger than R naught. So in this case, if you someone asks you to find out the CMRR, what you will find out is A output differential mode divided by A output common mode. Okay, since there is no output, since there is no output to input differential mode divided by A output to input common mode, and since there is no output common mode in this circuit, so there is no concept of A's common mode output common mode to input common mode. While in the previous circuit that we saw, there was this common mode voltage that was present. So there you would take a common output common mode to input common mode.
Yes, sir. Sir, if you want means common mode, see that it should be small, no, sir. How in design how we can change this thing? We can reduce the common mode gain.
Yeah, the common mode gain. One thing is that you should make this particular transistor's length large enough that your common mode, your output resistance of this transistor is huge. And in that case, you can get a better common mode rejection ratio. So in this topology, that is all you can do. If you want better common mode rejection ratio, you will have to have some different kind of topology, which we will see going forward.
Yes, sir.
Okay, till now, is there any doubt in this analysis?
Fine, sir. Fine, sir.
Okay, so if it is fine till here, we will get back to the original discussion that we were having. And the original discussion we were having on the fully differential circuit. In this fully differential circuit, so we had output as a resistive load, and here we saw our common mode rejection ratio was GM times R naught. Okay. And this GM times R naught, as we discussed, so be it the 5-part transistor that we have or this particular topology, in both the case, the maximum GM time R naught you can increase by basically maximizing the output resistance of the tail current, and that has its own limitation. As you keep on increasing the length to maintain some significant amount of current in this, you will also have to increase its width. And if the width and length are increasing, the parasitic capacitance on this node will keep on increasing and increasing. And if the parasitic capacitance on this node is increasing, even though you get a good CMRR at low frequencies, at very high frequencies, due to this parasitic capacitance, your CMRR will drop again. Okay. So, there is a limitation to this particular topology. So, what we can do is we can again re-examine how did we come to the GM times R naught equation of the common mode rejection ratio. So what we saw was that in differential half circuit, there was some current that was being pulled by the lower part of the circuit that was getting multiplied by the load resistance R, and it was resulting in GM times R for a differential half circuit. The same thing was happening for the common mode half circuit. Some current was being pulled by the lower part of the circuit, getting multiplied by the load R by 2 and resulting in this particular formula, that is R by R naught. Okay. We see that the load in case of both common mode and differential mode is same for this circuit. Okay, so if somehow we can make some circuit that has different load for differential half circuit and common mode half circuit, what we can do is we can try to increase the common mode rejection ratio. So let's say we intend a resistance of R over here, and we So this R will be a significant quantity because we need some gain in differential mode, and the load that common mode half circuit sees should be can be much smaller. If that is much smaller, so even though some current is being drawn from the lower side, since the load that the common mode half circuit sees will be much smaller, we can have a better common mode rejection ratio. The common mode gain will be less. So we'll try to build that particular topology. Okay. Did you understand my argument?
Yes, sir.
Can you repeat it?
Sir,
Can you summarize what did I say?
here the common mode gain we need to one minute, sir.
Okay, I will repeat it once again. So basically, in both common mode and differential mode circuit, some current is being pulled by the lower part of the circuit, and that is getting multiplied by the load, which in differential mode it's R, and in common mode it's R by 2. So if somehow we can make the load of the common mode circuit much lesser than what the differential mode circuit sees, then we can reduce the common mode gain and hence increase the common mode rejection ratio.
Sir,
Uh,
means by increasing how, how can we reduce the common mode gain?
I am telling you, we will look at next. So this part of the circuit remains similar. We have VCM plus VD by 2, some VB, and some output resistance R naught. Then we have VCM minus VD by 2. Okay. So let's say this circuit was like this. Okay. We have one circuit like this, and the other circuit, as we saw over here, that looks like this. The original circuit. So what is the looking in load in this case?
R, sir.
R. What is the looking in load in this case?
1 by GM.
1 by GM. Let's call this GMP because it's the GM of a PMOS. Okay. So what kind of load you want in differential circuit and what kind of load you want in the common mode circuit?
Sir, if in differential mode, if we have active load, we can get more gain.
No, no. Tell me from circuit 1 and circuit 2. Which circuit you will prefer for differential mode and which circuit you will prefer for common mode?
Sir, for circuit 2 for a differential mode
Circuit 2 for differential mode. Why?
because of 1 by GMP.
So in differential mode, what kind of load you want? You want larger impedance or lower impedance?
Input impedance should be large, sir.
Not the input impedance, the output impedance, the load impedance.
Yeah, it should be small, sir.
Why it should be small?
open, right? Sir, it should be large also. We
Why it
get
should
more
be
gain
large?
because it transconductance into output impedance, sir.
Correct.
So output impedance is more, we get more gain here.
Okay, so you want more to get more gain, you want larger output impedance or the load, correct?
Yes, sir.
So, now tell me which circuit you will prefer for the differential operation.
Circuit 2, sir.
Why?
No, circuit 1, sir. 1 by GMP is
Why?
less, right?
Yeah, 1 by GMP
Uh,
will be much lesser than the load resistance R that you intend to put.
yes, sir.
Okay. So, and which circuit you will prefer for common mode?
No, sir, I don't have idea.
So,
For
in
these things,
common mode, what kind of load you need? What kind of gain you need? You need lower gain in common mode, right?
yes, sir, we need lower gain. Circuit 2.
So, circuit 2, because it will have lower output impedance and hence it can help you get lower gain. Okay. So, we need to find out some way in which, while doing the differential circuit analysis, we see this particular circuit, and while doing common mode circuit analysis, we see this particular circuit. Okay. Now,
Yes, sir.
let's try to see how we can achieve that. So, we see that these two particular, the upper end of these resistors are grounded in terms of differential circuit.
Yes, sir.
So in differential circuit, what are the two ways in which we can achieve ground? One is by actually connecting it to ground. What is the other way?
Other way, you'll write small signal like
No, no, no. See, for example, if let's say this is some differential circuit, these are two different halves of a differential circuit. If we
hmm.
connect two equal and opposite swinging nodes with each other, that particular node becomes a differential ground, right?
Yes, sir.
Okay. So what we can do is this circuit, circuit 1 can be modified as follows. R, R, some output resistance ROP over here, and like this. Then this particular node will be a differential ground.
Yes, sir.
Okay. So now, so as far as differential circuit is concerned, this circuit and this circuit are equivalent to each other. Do you agree on that?
Yes, sir. Yes, sir.
Okay. Now, let's see circuit 2. In circuit 2, if I modify the circuit 2 as follows, if I just, let's say, I put two resistances of values R in this fashion, will anything change for the circuit 2? If these two resistances R are added, will anything change for this particular circuit?
There will be a change, sir.
What change?
Resistance is added, and
Yeah,
so
so what will
the
that do?
see the effective 1 by GM in series will R will come some.
Will there be any current flowing in this direction?
No.
So, if no current is flowing through this particular resistor, what will be the voltage across this resistor?
Yeah, 0, sir.
Yeah, so will it have any impact on the circuit?
Oh, okay, okay. No, no, sir.
Okay, so the load is still 1 by GMP.
Okay, sir.
Okay, now we need to so for differential circuit we need this thing. For common mode circuit we need this thing. Correct?
Yes, sir. Sir, that
Okay, so
how that R came, sir,
what? Which are?
for right circuit, common mode.
Yeah, so I deliberately inserted a resistor to see whether resistor has any impact on circuit 2. Like the circuit 2 and circuit this particular modified circuit, does it has any change? Like as far as its functionality is concerned so far.
Yes, sir. Okay, sir.
Okay, so I deliberately put that resistor. Now, how can we get this kind of circuit in this particular topology? What change we have to do in topology? Let's call this topology 3 and let's call this topology 4. What change we have to do in topology 4 to get the required design of topology 3?
So there should be a connection between upper transistors, sir. PMOS and PMOS.
Okay, so if we connect it like this, so what happens is, as far as differential voltage is concerned, this will become a ground.
Yes, sir.
Correct? This is a ground, this is a ground. So differential half circuit, it will be a resistor with ground on the top, then the input GM, the VD, and again ground. Correct?
Sir,
Hello?
R not will also.
No, no. This particular node has become ground. No, this is ground. This is ground. No current will flow through R naught as far as differential half circuit is concerned.
Yes, sir. Yes.
Okay, so this is there. Now, what will happen for the common mode half circuit? Will any current flow like this or
In
like
common
this?
mode, right?
Yeah. If there is only common mode swing, these two nodes will swing equally by the virtue of symmetry, right?
Mm.
So no current will flow from this node to this node.
So because of equal voltage.
Yeah, because the voltage is equal, no current will flow.
Okay, sir.
Okay. So if no current is flowing, it is equivalent of this thing. So if there no current is flowing through resistor, this is as good as this thing over here. Correct?
Mm.
Now if you again fold this circuit by the axis of symmetry, you get this thing over here. VCM and output resistance R0. So this is 2 GM. This is 1 by 2 by GM. Correct? You understand this?
Yes, sir. Yes, sir.
Okay. So what is the differential gain? It's still GM times R. The common mode gain is now if
2
this
GM.
is GMP, 2 GMP times, sorry, it's not 2 by GM, it's 1 by 2 GM. So 1 by 2 GMP times 2 GM, not 2 GM, times 1 by R naught. So 1 by R naught is basically, so VCM times VCM by R naught is the current that is being pulled by the lower half of the circuit. And the upper half, the load is 1 by 2 GMP. So it will be VCM by R naught times 1 by 2 GMP. You understand?
Sir, could you repeat again, sir?
So basically here, if this is VCM, what is this node?
Yeah, VS, sir.
What is VS?
Okay. Okay. GM or not? 1 plus GM or not?
2 GM R naught upon 1 plus 2 GM R naught.
Yes, sir.
Okay, which is roughly equal to 1.
1.
Okay, if this is 1, that means this is VCM. What is the current that is being flowed?
Yeah, VCM by or not, sir.
VCM by R naught. So what is the
Hmm.
voltage that is developed at the output VCMO? Current times the load.
Hmm.
So VCM by
Yeah,
R
VCM
naught
or.
times the load,
Hmm.
that
Yeah.
is 1 by 2 GMP.
Yes, sir. Yes. Yeah.
Okay, so we have GM times R times VD in differential half circuit, and VCM by 2 GMP R not in the common mode half circuit. So now you see that like in the same circuit, we have different output loads for both differential and common mode half circuit. We have a very small load for the common mode half circuit and a large load for the differential circuit.
Yes, sir.
Do you follow?
Yes, sir. Yes.
So
Yeah.
what is the CMRR now? It's GM times
GM
R
or. Yes, sir.
divided by 1
G.
by 2 GMP times R naught. Correct?
Yes. Yes.
So
GM into GMP 2 times out. R into R naught.
this will be sorry, this will be 2 times because just a minute. It's 2 GM, right? So okay, yeah. So it's basically 2 times GM times GMP times R naught. You get this?
Yes, sir.
What was the case previously? It was CMRR old was just only GM times R naught.
Hmm.
So it's basically GMP times R higher than the previous circuit.
Hmm. 2 times, sir.
Not 2 times. 2 times GMP times R.
Hmm.
And GMP times R will be a considerable gain. So basically, by using this particular topology, where this circuit 4 over here, you get different loads. You get a higher load for differential circuit, lower load for the common mode circuit, due to which you get a better common mode rejection ratio than the conventional, than the simple resistive load. Do you understand?
Yes, sir. Yes, sir.
Okay. So, any doubts so far?
Fine, sir. Yeah.
Okay. So, if there is no doubt, this was the content that I had for this time. And thank you for attending.
Yes, sir. Sir, 1 minute, sir. Normal.
Okay.
recording completed me.